Hi guys, up to now what we have covered is we have seen transformers, which was a static device and it converted electrical energy into another electrical energy but at a different voltage or a current level. Then we saw DC machines, which were generators and motors and worked on DC supply, or DC generator generated the DC output. Then we saw synchronous, which was the first AC machine that we saw. And why is it called as synchronous? Because it rotates at a synchronous speed. Okay. In case of generator, the frequency generated depends on the rotor speed, and in case of motor, the rotor speed depends on the frequency applied to the stator. So, in this lecture, we will be starting with induction machines. As the name suggests, it works on the principle of induction. Like in case of transformer, there is induction between primary and secondary. Similar way, in case of induction motor, there is induction between stator and rotor. Okay. So, first of all, induction machine is a singly fed machine. Singly fed means there is only a single source which is applied at the armature. So, we apply a three-phase supply at the armature. Okay. And on the field winding that is there on the rotor, the field or the current will be induced, or the energy from stator to rotor will be processed via induction. So rotor is not given any energy, it will get its energy from the stator by means of induction. Okay. So here first of all a three-phase supply is applied to the stator, which will produce a rotating magnetic field, which will induce currents in the field winding, which will generate another magnetic field. So we are applying only one magnetic field, that is the stator magnetic field. So stator field will lead to rotor field. Okay, rotor field is not generated by itself. Like in case of synchronous machine, what was happening? We were applying a DC source on the rotor. So that was generating the rotor rotating magnetic field. And we had three-phase supply on the stator that was generating stator magnetic field. So both the fields were independent of each other and both rotated at the same speed, that is the synchronous speed. Here we are applying only one magnetic field and other field is getting generated from the first field. Okay, that is how induction motor works. So why is it so popular? Because see, the distribution system is entirely AC. Okay, that is, it works on alternating current. That means we need the motors that work on AC. So the first motor that we saw that worked on AC was synchronous motor. But the problem that we saw with synchronous motor was it was not self-starting. But induction motor, it is self-starting. Okay. Also the cost of induction motor is pretty low. That makes it even more popular. And here also the speed control is possible. Like in case of DC motor, we can control the speed of induction motor. So if we want to generate a variable speed drive, that is a motor that rotates at variable speed, but it should be AC motor, then induction motor is a preferred choice because its cost is low and it can provide speed control as well as it is a AC motor. That is why induction motors are so popular. So let us first understand double revolving field theory. In case of synchronous, we saw revolving field theory. That is applicable here also, but double revolving field theory is an alternate way of explaining the rotating magnetic field. Okay. According to double revolving field theory, what does it say? The MMF due to single phase can be resolved into two oppositely rotating MMF waves at same speed. So what I am saying is, suppose one MMF we take, let us say FA, it is FM cos theta cos omega t. Here theta is space angle, that is the angle that when the rotor rotates, the angle of the rotor will change. that will be called as space angle. The angle made by the rotor in space. That is my theta. Okay. So here what I am assuming is flux is sinusoidally distributed in space as well as it is sinusoidally varying with time. Okay. Ideal distribution of MMF or flux is sinusoidal distribution in space. Okay. That is what we want to achieve always. Now we can break it something like this. Fm by 2 cos A cos B can be written as cos of A plus B plus cos of A minus B. Okay. Out of this, theta plus omega t represents backward rotating and theta minus omega t represents forward rotating. So this is forward and this is backward. Okay. So we have one forward rotating MMF, one as backward. So this will be represented as Fa negative plus Fa positive. Positive means the forward rotating, negative means backward rotating. Okay. Similarly, for B phase, it will be Fm cos theta minus 120 because the B phase will be kept at 120 degree in space from the A phase. The three phase windings are space displaced as well as phase displaced by 120 degrees. So this will be Fm by 2, then cos of, if we subtract these, theta minus omega t, and if we add these, theta plus omega t minus 240. So this will become Fb positive plus Fb negative. Similarly for C phase, Fc will be Fm cos theta plus 120 cos omega t plus 120. So if we break it again, Fm by 2, if we subtract these terms, cos theta minus omega t plus cos theta plus omega t plus 240. Okay. So it will be Fc minus plus Fc positive. Okay. Whenever there is a negative sign between theta and omega t, it will be forward rotating wave, and positive sign between theta and omega t will represent reverse rotating or backward rotating wave. Now to find the total flux, it will be Fa plus Fb plus Fc. Now this forward rotating wave is same in all the three cases, so it will become 3 by 2 cos theta minus omega t. But what about backward rotating? It was theta minus omega t in case of A, so let us say Fa negative. In case of B, it was theta plus omega t minus 240. Minus 240 means this way, and plus 240 means this way. So all these three are oriented at 120 degrees, so the net will be 0. Okay. So we have only forward rotating wave, that is my revolving magnetic field, which has a magnitude of 3 by 2 times Fm. That we saw even in case of rotating magnetic field. That is how the rotating magnetic field is generated. So double revolving field theory is more important as compared to rotating magnetic field because it shares or it tells us the nature of single phase MMF. In rotating magnetic field, we directly saw the three phase. But when we study single phase induction motor, then this theory will come into picture because there will be only single phase. So there will be two oppositely rotating MMF waves. Okay. So keep this in mind. A single phase produces two oppositely rotating magnetic fields, but when we sum it over three phases, then negative rotating magnetic field gets cancelled out and only positive remains. But here if we change the phase sequence, then what will happen? The positive sequence will get cancelled out and only the backward rotating wave will remain. And that is what we studied in rotating magnetic field also. Changing the phase sequence changes the direction of rotation of the field. So here if we change the phase sequence, forward field gets cancelled out and backward field remains. Okay, so that even double revolving field theory also explains. Next, let us come to the construction of the induction motor. So the first part that we are seeing is stator. So here stator is made of cast iron. Okay. As I told you, induction motor also works on the same principle as the transformer. But in transformer we were using CRGO steel. Why are we using cast iron here? The thing is, in case of transformer, between primary and secondary, we had the entire magnetic material. Okay. So reluctance between primary and secondary depended largely on the magnetic material reluctance. But in case of induction motor, this is my stator and this is my rotor. So there is some air gap. Okay, and we know permeability of air gap is mu naught. So its reluctance is high. Because permeability is low, reluctance is high. So reluctance is mostly determined by the air gap between the stator and the rotor. Okay, because the major reluctance comes from the air gap, since the air gap reluctance is very high. So no matter what type of material do I use for stator and rotor, the reluctance will depend on the air gap between the stator and the rotor. So that is why we try to choose a lower cost material, okay, or a cheaper material, so that cost of the motor can be minimized. And as I told you, one of the advantages of induction motor is it is a very low cost motor. Okay, so to achieve low cost, what we do is we choose a lower cost material, that is the cast iron instead of CRGO steel, because anyways the reluctance will depend on air gap. Okay, and here stator is made of laminated silicon steel. Why we do lamination? To minimize the hysteresis and eddy current losses. Okay, mostly lamination reduces the eddy current losses, so we use a laminated silicon steel. And the use of silicon steel reduces the hysteresis losses because it increases the resistivity as well as it narrows down the hysteresis loop. So here we are saving the cost by using a cheaper material. Okay, now to place the windings in the stator, we have to create the slots. Okay, so when we create the slots, there are three types of slots. First one is called as open type slot. Here the face of the slot is open this way, and this is the coil that I have placed in the slot. So here what happens is air gap is more between stator and rotor. Due to this type of slot, air gap is high. If air gap is high, then what will happen? The reluctance will also be high because it is L by mu A. Okay. More reluctance will cause less reactance. Reactance is N square by reluctance. So as reactance increases, reactance reduces. Okay. And for the same value of flux, flux is Ni mu by reluctance. If flux is constant, then I mu should increase for compensating the increase in reluctance. I am assuming that flux remains constant. If flux is constant, Ni mu is phi into reluctance. So as reluctance increases, I mu also increases. And as we saw in case of transformer, as magnetizing current increases, the power factor reduces. Magnetizing current always reduces the power factor. Okay. And here the flux is non-uniform. If flux is non-uniform, then what will happen? The flux is non-sinusoidal. That is, it will contain some harmonics which will cause harmonic torques. And if there are harmonic torques, then there will be noise and vibration in the machine. Okay, that is why open slots are not preferable for the induction motor, because here flux is not sinusoidally distributed in space and it will cause noise and vibration in the machine. Now suppose we tilt the air gap. We tilt it like this so that it is not fully closed and it is not fully open. So it is called as semi-open. Okay. So here we have reduced the air gap. So air gap, let us say G, reduces. So reluctance, which is G by mu A. As G reduces, reluctance also reduces. As reluctance reduces, Ni mu, which is phi into reluctance, magnetizing current reduces. As I mu reduces, it will lead to increase in power factor. It will make the flux a bit more uniform. Okay, because the distortion in flux was caused due to saturation and the role of hysteresis. That is why in transformers we saw that the flux became non-uniform. Okay, so flux will be more uniform here. That means harmonic torque will be less. This is TH. TH means harmonic torque. It will be lesser in case of semi-open type of machine. That means the noise and vibration will be lesser if we use semi-open type of slot. And the last type of slot is closed slot. So here what I have done, I have closed the slot and placed the winding inside. The problem with these type of slots is once we have closed the slot, we cannot access the coil. Suppose the coil gets short circuited or coil gets damaged, I cannot replace the coil because I am not able to access it. Okay, so here no access to the coil. Okay, now here air gap is minimum. Since air gap is minimum, its reluctance will also be minimum. If its reluctance is minimum, its magnetizing current will also be minimum, or its power factor will be maximum. So power factor of a closed type of slots is maximum as compared to the open and the semi-open type of slot. Here flux is also uniform. So harmonic torques are minimum. Okay. But here what happens is the leakage reactance is highest. Why? The thing is, here there will be lot of leakage flux, the flux that will not be linking to the core. So here leakage flux increases. Okay, if leakage flux increases, what will happen is, we know that lambda is equal to Li. So as leakage flux increases, leakage inductance increases, due to which leakage reactance also increases. That is undesirable. Okay, leakage reactance or leakage flux should not be very high. Otherwise, what will happen is the performance of the machine will suffer. We do not want the flux to be leaking. We want maximum flux should link between the stator and the rotor. Okay, so open type has one disadvantage, that it requires more magnetizing current, so power factor of operation is low. The closed type has other disadvantage, that it has a highest leakage reactance or it has the highest leakage flux. So that is why we go for semi-open type of slots for the case of induction machine. But in case of DC and synchronous, we use open slots because open slots have maximum air gap. For maximum air gap, the reactance will be lowest. If the reactance is lowest, then what will happen in case of synchronous machine? We saw maximum power was EV by X. So as reactance is X, reduces, maximum power will increase. Okay, so that is why the stability of machine will also go up. In synchronous, the critical design criteria is stability. So to improve the stability, we use open type of slots which have more air gap and hence lesser reactance, so more power transfer. Okay, And here also, as in case of synchronous machine, we will use distributed and the short pitched winding on the stator side. Okay, so the stator construction essentially remains the same, just the nature of stator slots changes. In case of synchronous, we use open type of slots. Here we use semi-open type of slot. Closed slots are never used because then we will never be able to access the coil. Now let us consider the construction of rotor. So the rotor that we studied in case of synchronous were salient pole and the cylindrical. Here the rotor is called as squirrel cage induction motor. In squirrel cage, what we have actually is we have conductors like this. This is one conductor, other conductor, third conductor, and these are all short circuited. Okay, here instead of any winding we have conductors. So whenever the magnetic field will cut these conductors, an EMF will be induced. Okay, but we want some current to be flowing in these conductors. Why? Because a current carrying conductor placed in a magnetic field will experience a force. That is what my Lorentz force law is. So I want the rotor to rotate. That means I want the rotor to experience a torque or a force. So it must carry some current. And for current to flow, we need a closed path. So EMF will be induced in these conductors, but to make a closed path for the flow of current, we short circuit these conductors on both sides. This short circuiting is done by means of end ring. End ring is made of same material as that of conductors. Usually these conductors are made of copper and aluminium. That means we need end rings also of the copper and aluminium. Here air gap is lesser, so reluctance is also lesser. In case of squirrel cage, we have less air gap, so lesser reluctance. Okay, so lesser reluctance means lesser magnetizing current, which implies higher power factor. So it operates at a better power factor as compared to other construction of the rotor. So since it operates at a better power factor, that means its running characteristic is good. Okay, running characteristics are good for the case of induction motor. But the thing is, in case of induction motor, we will derive later on that when we start a motor, a starting torque is produced which depends on rotor resistance. Okay, so here since we have short circuited both the sides of the bars, we cannot insert any external resistance. Okay, the resistance of rotor is fixed. That is why the starting torque is low in case of squirrel cage induction motor. That means its starting characteristics are poor, but its running characteristics are superior since it operates at a lower magnetizing current and a higher power factor. Okay, and to make the flux uniform, if you see, the conductors have been tilted. They haven't been placed straight, they have been tilted. Why they have been tilted? Here we are skewing the conductors to reduce the harmonics, as we saw in case of synchronous machine. By skewing the slot, by skewing the conductor, what we can do, by skewing it by 2 pole pitch or 2 harmonic pole pitch or 1 slot pitch, we were reducing the harmonic content. Similarly here I am reducing the harmonic content by skewing the rotor conductors. So by reducing the harmonic content, we will reduce the noise and vibration in the machine. Okay, so remember, squirrel cage has very good running characteristics. It operates at a much better power factor, but its starting characteristics are poor since it produces a less starting torque. So let us summarize what we learnt in this lecture. We first saw the basic of induction machine. Why is it called as induction? Then we saw the double revolving field theory or DFR. There we saw one MMF or MMF due to a single phase can be resolved into two oppositely rotating MMF waves, one of which rotates clockwise, other rotates anti-clockwise, and both rotates at the same speed, that is the synchronous speed. Then we saw stator construction. We saw three type of slots: open type of slot, semi-open, and closed. In open, the problem was air gap was high, so the machine would draw more magnetizing current, which will lead to a lesser power factor. So it will have poor running characteristic. In case of closed type of slot, leakage flux was very high, due to which the flux linking the stator to rotor will be lesser. So that will also reduce the torque produced in case of a machine. So that is why we go for semi-open type of slots, whereas in synchronous and DC we will go for open slots. Why we go for open slots? To increase the stability of the machine. Then we saw squirrel cage induction motor. The rotor has conductor bars made of aluminium and copper, and here these conductor bars are short circuited on both ends for to permit the flow of current. But due to this short circuiting, we cannot add any external resistance, so starting torque is reduced. So it has poor starting characteristics but excellent running characteristics, since air gap between the stator and rotor is quite low in this case. Okay, so that is what we learnt in this lecture. In next lecture, we will see other construction of the machine, that is the wound rotor, and we will study about the working of the induction motor. That is, how does the induction motor produce the torque and how does it operate. That we will cover in the next lecture.